everyone, and welcome back to Code and Cognition, where today we are looking into the first video of Linear Algebra series for machine learning, where this first notebook that we have here, we'll go through this all in detail. But on the first glance, you all can see that this is just a basic concepts that we'll be requiring throughout the linear algebra, and scalars, vectors, tensors, or etc. And in the second notebook that we are going to see are some concepts that are required, that are necessary in the world of machine learning, which we'll see very briefly the application of such and how they are being computed, etc. Uh, as that's the main goal. And yeah, so yeah, let's get started with the actual explanation, implementation, and visualization uh, of the so let's get started with the actual visualization, implementation, and the code for the first video that we have. Uh, so this is the first cell that we have, which is just importing NumPy, Matplotlib, and Seaborn, and printing if whether or not we have these libraries ready in our session that we are running right here. This is all in Colab, by the way. Uh, So yeah, so the second part is where we are trying to introduce the scalars, which is the atomic unit. Let's just assume, where the scalar is just basically a single number. It does not have any dimension written to it. Like we can just say age is 25, temperature is 72 degree Fahrenheit, or accuracy is 0.94. So these are some scalars that we are going to print. Mm. See, but ML, the problem that we are trying to figure out here is that ML needs multiple features. We need age, income, location, time, device, blah blah blah. So we have to now enter vectors. So from what we can see, from what we can see is that we require uh, just not the scalars, but we also require vectors, which is an ordered list of numbers. Just putting it very simply out there, it is like an ordered list of numbers which organizes multiple numbers together. So like algebraic and geometric, both parts we'll see. Well, algebraic, let's say this is one of the view, and geometric is this is an arrow in the space. So but we use algebraic mostly because visualizing all of this in more than 3 dimension becomes really complex, and we deal with at least hundreds of thousands of dimensions, at least thousands of dimensions in machine learning. Don't get surprised when you'll see such big numbers in there, with such big numbers being used as vectors. So yeah, so this is a customer as a vector where we are taking age, income, urban, time, whether they are urban, the time of minutes, and the mobile number. And the customer vector, this is a customer vector. Now this is how the ML data is stored. So this is the customer vector. Age is 28, income is 75K, urban yes, time for 45 minutes, and mobile number yes. I'm just keeping high and low, where one signifies that yes, the number is there, is present, is not printing the actual number, and that's how. This is a basic idea of how this is being done, and then we move on to do visualization of the customer in 2D. But now we are using the NumPy functions to make these. With these are just plots. You all can go through the code in detail. But what my intention here is to show you all that this in itself is the customers as the vectors in 2D space. This is in 2D space actually, where the customer is new, customer A, customer B, customer C, where these are the customer A, this is customer B, this is customer C, this is customer, which is the new one. So now this data can be represented in geometry way. Closer points means more similar, as we can understand. These two things are closer, these two users are close, so this may be similar. Yeah, so there are a lot of correlations, causations, issues which we'll cover later. So finding the nearest neighbor is one of the methods. This is again we're going in very brief uh, approach. We'll go in detail later, where we are finding the distances from the closest neighbor. Where to A 5.83 is the nearest distance, where we are calculating this using these functions. I hope you all know these. If not, we'll make a separate video on this. But yeah, so basically we're calculating the distance between the customers of new and zero, new and one, customer one, and new and customer two. So once this is being done, we find out that to A, the distance is the nearest, which is 5.83. To B is the 38.91 and 70.35 to C. So this is the K nearest neighbors. Applications of these can be found out in classification, recommendation, and cluster, which we will look into definitely later on. Not in, if not in this video, then in later videos. So now we have vector operations, as we must have all studied, which is like you can add a vector, you can multiply it, scalar, you can visualize this, you can add. This is just the visualization part of it. Yeah, so like u is this vector, v is this vector. So if you add u plus v, you get just let's just get it in the visualization. The u, this is v, and this is the addition of these vectors. And this is the scalar multiplication of the vector where I multiplied this two times. And this is how it is being shown. So matrices can be used for storage and transformations, as we have understood till now, that 2D arrays of numbers. Two views, as we saw, data storage, rows is equal to samples, columns is equal to features. As you do it the opposite way, there may be some issues. But this is a general notation. Transformation function that changes these vectors. So let's say we have this matrix as a data set that we have here, data, and yeah, so four customers into five features. So every ML dataset is basically a matrix. Basically, this is how the data is being stored through arrays and these functions. So NumPy function is also quite crucial. Uh, so matrix as transformation, we'll see here. These are the, we are scaling it by two. This is another vector v transformed is equal to a. This we won't go into detail. This is the visualization part. This is matrix A. This is vector V. So A at V is equal to 6. This because this the vector was scaled by 2 after matrix transformation. Uh, these notations we'll look into in depth later on as well. So this is the neural, and this is just giving you a basic overall understanding of how it works. In depth, we'll be covering in this part of the video. Uh, Neural networks of matrix multiplication, well, a single neural net, and this is again going to be covered. So let's say we have a neural layer function where you are defining it and linear activated value. Uh, so yeah, uh, this is a subsection where this defines the layer. This is the example, and then nodes where this is basically the weights that we have and the output of the two neurons that we have, 0.55 and 0.58. Every layer is basically this, where learning is adjusted between weights and biases. Linear algebra is basically neural networks that we have understood, and we will look into this in depth. This is just to give you an overall view of how it works. Okay, so there is basically much more to linear algebra than just 2D, as we can figure out on our own. That the till where now what we have seen is basically just two dimension, and we'll be looking into more than two dimension, where we call it as a tensor. So like tensor is 3D, 4D, 5D, etc. Now this is a grayscale image, color image is 3D, images of images could be in the 4D. All of this we'll be looking into, but in terms of this, we are looking only at a 2D matrix and a 3D tensor. Um, Tensor dimensions in deep learning could be grayscale looks like this, color image looks like this. These are the notations, by the way. This is height, width, and this is the color. This is the this all will be covering text. In text bird, we use this as a batch. This is the sequence length, and this is the embedding. And yeah, so all vector and matrix operations can extend to tensors as well. This is the basically the transformation that we have from 2D to 3D tensor, 2D matrix to a 3D tensor. And here we have the one of the essential concepts of linearity, where a transformation T is linear. We understand that by if we have these two properties, you can see this on your screen, uh, where this is the additivity and homogeneity. These are the transformations can be done if the transformation can be done is called linear if these two function conditions are satisfied. So we can test the linearity again of this, test the additivity, homogeneity, and then print that. So let's say we have a left and right. So this is additivity, it's true, and yeah, so homogeneity is also true. So matrix multiplication is linear. Why it matters, as we can understand, is that it can decompose problems into smaller pieces. Efficient computation can be done. Mathematical tools are available for this directly. So you all can easily do those calculations. We'll look into this in depth later on as well. So the journey ahead was made as just a uh, thumbs up for you all. And yeah, so these are the exercises you all can do. Create a vector for three products, like let's say price, rating, and number of reviews that it has. Uh, yeah, so these are the three products that we have. Product vectors created. So just create three vectors for the three products. One of this is being done for you all already. Find which products are most similar that we have seen. Then we can calculate the distances. Then normalize the features to 0, comma 1. Again, you all can do this. And yeah, so I want you all to do this part on your own. The notebook will be shared in the comment section, so please go through this. So just a summary, linear algebra is the language of ML, scalars, vectors, matrices to tensors. This is all a brief overview of what we have seen, little bit of glimpse of the applications as well, which we'll look into over here as well. Neural networks is basically matrix operations with weights and biases, everything else to be taken into consideration as well. So we'll look into that. We understand data is geometry, similar is closed in space. Algorithms are transformations. That's what we understand as well. Uh, yeah, so everything is basically linear algebra from your like, k nearest neighbor to your chat GPT that you chat with can all be broken down into a linear algebra as well. So yeah, let's move on to the next thing that we have. Now this is a little bit in depth of an operations or what you're going to see right now. So let's just get started with that. Uh, so yeah, but we are here to understand the maths, the CS concepts, the ML parts, the research application, and the engineering and optimization part of linear algebra, the applications, the formulas, and everything. So this is just I'm setting up my environment here. Uh, yeah, so this is just printing the version number and the libraries that are present. So if you have these libraries, you can go ahead. This is just a safety check for you. So we have the formal definitions of scalar and vector. We primarily work with R for a scalar of field F, typically R or C. Vector V is R raised to n, where R is an ordered n tuple of real numbers. So tuple, I hope you all know tuple. Can be covered in Python. You can go back and read that. Ordered n tuple of real numbers. So we have now vector space where a set V with operations is given as this, where V is a vector space if it satisfies these conditions: closure under addition and scalar multiplication, associativity, commutativity, and all of these conditions that you can see right here. These are just the formal definition. We'll look at their application below. So now we have a matrix M cross N, where of matrix A, M cross N is a rectangular array that we can see right here. Uh, and a linear transformation can be said R raised to N is transformed to R raised to N is linear if we satisfy this condition, again, which we will see down below. So as you all can see, this is U and V is multiplied by coefficients alpha and beta. So again, this is split into two, split from here, and then where alpha and beta are real, U, V are also R raised to N, which is this the original thing that we had. So, and this is the computational complexity, again, a good thing to keep in mind. Next time you'll go through this, just screenshot this or go through this in detail. But yeah, so these are the complexity, time and space complexity with their dimensions as given here. We'll be going into details later, but just a quick heads up to give to you all. we have this. Why this matters is basically because training a neural network is just not a very small condition where we do this. We train a neural network over billions of matrix multiplications. LLM inference is basically O raised to big O of n square, where that signifies the attention mechanism that we have. Real-time systems, computational budget constraints are there. Hence, if we, this is like for real-time systems where we understand that we need to simplify the operation that we are running. Like as here we have the SVD, eigen decomposition, matrix inversion, etc. So okay, so now moving on. Let's move on to the benchmarking vectorization versus loops. This is the major part where we understand why is vectorization such an important concept. Again, we skip large sizes for loops because it's too slow, which we'll see down below. As you all can see, this is the Python loop and this is NumPy vectorized. So basically, time in seconds can be seen where if the vector size is significantly small, then the difference in seconds is not that much. But as you all increase the number of loops, the time in seconds, the difference in the time uh, is quite drastic. As you all can see, the performance comparison can be seen over here. Uh, as and as we increase it by power of 10, this is the actual faster performance with the vectorization. So vectorization uses SIMD cache locality and avoids Python interpreter overhead. Always vectorizing production is the key takeaway from here. We'll go into depth again in the later video. This is just the main objective of the video is to make you all get interested in this field of linear algebra, and we'll be diving into it later on as well. There are some vector norms and distance matrices. Again, you all can pause your screen and read these norms on your own special cases. So a norm on vector, okay, so just to explain, a norm on vector space is a function this where satisfying these conditions with equality if and only if v is equal to 0, positive definiteness and homogeneity is there, triangle inequality is there, and common norms are such. This is the formula. And special cases is Manhattan, Euclidean is one of them, Max is one of them. We'll see the visualizations. And ML applications can be seen in the regularization, as we can see here, induces sparsity, range for smoothness, distances can be guessing, KNN clustering anomaly detection, loss functions. We can see this in loss functions as well. Uh, Gradient clipping, this is done to prevent exploding gradients in deep learning. Uh, yeah, so this is that, and this is some visualization that we'll be seeing on some norms that we see. This is the L1 norm, Manhattan one. This is the Euclidean norm, and this is the max norm. Again, these are just to provide yeah, spark some interest. And norms of vector 3 and 4 again, as you can see, uh, is given as this. ML applications are unlimited, unbound. As you can see, the amount of engineering that you can put into ML would always help out in with these tools in your pocket. So memory layout is cache efficiency, row versus column measure. Uh, Again, some concepts to see, NumPy C order, which is a row measure. Memory is kept like this, where matrix is kept like this. So Fortran or MATLAB F order is column measure, where we keep it like this. Cache performance, modern CPUs is basically 64-byte cache lines. Sequential access is 100x faster than random. But matrix operation layout matters for speed. So implications from this we can see is that iterate over rows and not columns in NumPy. Transpose can be expensive if data is copied. Block algorithms for large matrices is the thing. So memory layout and performance impact of the same. We can see we have created a large matrix and cache performance test is done on the same. So this is a large matrix that we have taken and done a cache performance test on the same. The ratio right now for a 10K into a 10K matrix would be sum over rows, which is cache friendly, is 0.734, and sum over columns is 0.848. The ratio is 1.16x times faster. This is some production tips to use. Always I'll suggest go through documentation of libraries on your own. That will help out a lot in the future. If you all want, we can make a video on that as well. So we have NumPy's next thing, which is the broadcasting rule, where two arrays are compatible for each dimension if it satisfies these conditions, and it works. It fails in these conditions. Why does it matter? Is because this is working. Broadcast this to 1 comma 4 4 comma to 1 comma 4, and this can be broadcasted. Basically, it just says that if two arrays are compatible for each dimension, if these conditions are satisfied, this is one of the most important part. And it fails in these conditions because 4 is not equal to 3, uh, uh, and 2 is not equal to 4. So why it matters is because it avoids explicit loops, memory efficient, not copying, no copying as such, and faster execution, critical for batch processing. Again, all of these concepts to be seen on later. Uh, Broadcasting, some practical examples we'll be running here. So this is row normalization from 5 comma 4. This is the metric shape with these things in it, and row means shape is this. uh, Again, row means after centering could be this, but broadcasting example after pairwise distances. For loop version is this, broadcast version is this. The speed up is 152.1x. So again, sometimes batch broadcasting is really helpful because it helps in faster execution, memory efficient, and avoids basically explicit loops which are not required. And so yeah, so this helps out in these conditions because row means after centering becomes like this. So the speed up is, this is quite an edge case to be seen, but can be found out quite commonly. So broadcasting enables vectorized operations essential for modern ML frameworks, as we can see. So we've got a dot product foundation for a lot of things that we'll be seeing. Again, standard 12th mathematics. Again, you can stop and see the screenshot and can see the projection formulas, the cosine similarity formula, and the definition of it. Where basically it is like if we do u vector dot v vector, we will get the magnitude of u vector into the magnitude of v vector times the cos theta, which theta is the angle between uh, the two vectors. So again, we can see some edge cases or some special cases as we will call it, and the dot product application as we can see. So again, vector projection via dot product can be done. So if this is a vector u shown like this, and this is the projection of vector u on the x-axis, as that's just the legend given over there. Research applications can be seen for attention mechanisms, transformers slash LLMs, scale dot product attention scene. Again, quite won't go into depth here, but this is the attention weight matrix for the same uh, sequence length. Uh, this is the visualization part. We have scale dot product attention. Uh, as this, we'll go into depth over here as well. But the key position to understand here is that each row shows which position a token attends to. Each row which token it's attending to, and this is the core operation in GPT. Uh, uh, BERT and other models that we have. And modern optimization is that like flash attention reduces memory from ON squared to ON, which is a very big uh, enhancement. And okay, so moving on to the next thing, again in research applications is LoRA, which is low rank adaptation for LLM fine tuning. Problem we have here is that fine-tuning large language models is in billions of parameters requires updating all weights, massive GPU memory, and long training times. So instead of updating this, this is the basic formula. This basically does is parameter reduction. So let's say original parameters was 16 million, it reduces this to 65,000 parameters, which is 256 times fewer, which is 16 square times fewer. Uh, it's just how it works. You all can go through the formula and uh, implementation later. So again, these are things which we'll cover. Uh, LoRa implementation is something you can see, but efficiency analysis is given over here for certain models, as we can see, parameter count versus rank for each one of these. Real world impact, you can fine tune a 7 billion model on your consumer GPU, which is a 24 GB. GPU can be said RTX 4090 probably can be done on this. Quantization, again, efficient in inference. Again, as we see, problem is that LLMs are huge. We reduce precision of the thing where yeah, the precision is given in floating point 16. Again, you can reduce it to integer 8, integer 4, or even a single bit uh, accuracy, precision as well. Sorry. This is the quantization formula where S is the scale factor and Z is the 0 point, and we minus 0 point from the floating point 32 and divide the whole thing by the scale factor and round it off, and this is the x of integer 8. This is the precision levels. As we can see, the memory range is this, but again the precision level falls drops down. Memory is taken up quite significantly less. So memory is like 4 to 8 times reduction. So accuracy would be minimal loss with proper calibration is done. Speed is faster, but again memory can be seen to have a drop down. So again, this is quantization examples that we have. This is the demonstration. So I'll just run through this quickly. This is the quantization examples in front of you. Memory savings is 75%. 0 point is 1 to 129.5 for this particular example that we have taken over here. Uh, Again, reconstruction error, MAE is 5. So all of these things you all can see, right? So the real world applications of these things can be seen in GPTQ, GigaML, Llama.cpp, edge deployment for mobile phones and IoT devices, and cost reduction through cloud inference savings can be seen. So matrix multiplication is also like some kind of a can understand as styling for performance, where naive algorithm is like basically just poor cache utilization, but tiled and blocked algorithms is basically where the benefits of such things are like tiles fit in L1, L2 cache, is cache friendly, reduces memory traffic 10 to 100 times faster than naive that we have seen just here, these algorithms. And these are the tile slash block algorithm where this is just 10 to 10 100x faster than naive. And foundations of BLS AS libraries, which again we will see. GPU implication is thread blocks, process tiles, shared memory for tiles, tensor cores optimized for specific sizes, flash attention, tiles attention computation, reduces HBM accesses from ON square to O of n, and enables long context LLMs. So yeah, again, matrix multiplication. This is a demonstration for the same. You can see the matrix size of 200 into 200 can be seen. Correctness is true, but the tiled and the NumPy optimized BLS has these execution speeds. And NumPy uses heavily optimized C slash Fortran. Uh, our Python tiled version is still faster than naive. Uh, GPU kernels use similar tiling principles. We'll see all of this later. Sparse matrices handle scaling, handling scale. Again, as we many real world matrices are mostly zero. Graphs, adjacency matrices, NLP, neural networks. Again, very big numbers that we'll be dealing with, and sparse storage formats with the coordinates CSR is compressed sparse row, memory savings, and application in graph neural network, sparse attention, model tuning, federated learning as well. So sparse, this is just the demonstration of the efficiency that we have. And yeah, so the density is such non-zero elements were 100,000. So density becomes 0.1%. So the savings, again, this is an edge case, but the savings here become 99.7%. Uh, and sparse matrices vector multiplication is really small, and dense would take zero point 0.1 second, which is for 100 million operations. So real applications is like a web graph where 10 plus billion nodes are present, page rank, recommended systems, user item matrices, graph neural networks, sparse attention and transformers. So comprehensive summary of what you have done is also present in this some notebook. And the complete picture is also present. We will go through this later. These are some of the exercises which I think you all should go through.